From the law of chemical equilibrium, we already know how to write down the expression for the equilibrium constant for any reaction. Suppose we have a reaction in which A moles of A combines with B moles of B, giving C moles of C and D moles of D. The small a, b, c and d are the coefficients of the reactants A and B and the product C and D. Now from the law of chemical equilibrium, we already know that this equilibrium constant, which is K equilibrium, the symbol is K equilibrium, can be expressed as the product of molar concentration of the products raised to the power their stoichiometric coefficients upon the product of molar concentrations of the reactants raised to the power their stoichiometric coefficients. So K equilibrium will be equal to C to the power C into D to the power D upon A to the power A and B to the power B. I think you all will be knowing that whenever anything is expressed in the square brackets, it is indicating the concentration, which is always expressed in moles per liter. So it is molarity. Now this equilibrium constant is of basically can be expressed in two ways. It can be expressed in terms of concentration, we call it Kc, and if it is expressed in terms of partial pressures, it's called Kp. So it is Kc when all expressions are in concentration, that means in molarity, and we write Kp when all expressions are in partial pressure. We use partial pressure when the reactants or the products are gaseous in nature. Then we use this kind of equilibrium. Let me explain this to you with the help of an example. Suppose we have a reaction like nitrogen combines with hydrogen to form ammonia. Since all these are gases, but we can express their amounts in terms of concentration. So when we are expressing their amounts in the terms of concentration, we will call the equilibrium constant as Kc, and it will be then equal to the product of the ammonia, concentration of ammonia raised to the power 2 because its coefficient is 2 upon, since there is only one product, so we'll write only one, upon the concentration of nitrogen, and since its coefficient is 1, we'll not write anything here. Product of this will be done with the concentration of hydrogen, and since its coefficient is 3, we will do the cube of this. This is the expression for the Kc for this reaction. This is the expression of equilibrium constant in terms of the concentration of all the reactants and the products, and it is called Kc. So now you people know how to express this equilibrium constant in terms of the concentrations of the reactants and the products. Remember, we will be using this expression or this Kc whenever the reactants and the products are given in terms of their moles, and we will divide it by the volume, which will be the total volume of the vessel, because all these three are gaseous in nature. So basically we can also write down the same thing in terms of the number of moles of ammonia upon V to the power square number of moles of nitrogen gas upon V and number of moles of hydrogen gas upon V to the cube. Don't forget to divide the number of moles by V, because unless you divide the number of moles by V, then only it is the concentration, else it will not be a concentration. So your expression will be wrong. So it is the Kc in which we are expressing the reactants and the products in terms of concentration. Suppose the reactants and the products are in the numerical or in any particular situation are not expressed in terms of their number of moles. Rather than they are expressed in terms of their partial pressure. Then the equilibrium expression cannot be expressed or written in this way. We will write down in those cases the equilibrium expression in terms of partial pressure. So see, equilibrium constant in terms of partial pressure can be written as Kp, which is the symbol P is in the subscript, is indicating that we will be expressing the equilibrium constant in terms of partial pressure of all the reactants and the products involved. So it will be Kp partial pressure of ammonia to the square partial pressure of nitrogen and partial pressure of hydrogen and cube of this. So in place of concentration, we'll be using the partial pressures. And this kind of expression, when we expresses the amount of the products and the reactants available at equilibrium in terms of their partial pressures, is called equilibrium constant Kp. P is indicating this is in terms of partial pressure. Remember, these partial pressures are not your initial partial pressures. These are your partial pressures at equilibrium. So your P ammonia, P nitrogen and P hydrogens are your partial pressure at equilibrium. In a very similar way, the ammonia, nitrogen and hydrogen which we have expressed in terms of Kc were the concentrations at equilibrium, not the initial ones. So when it is expressed in terms of this, it is called Kp. Let us understand the Kp and Kc with some more examples. Like, let us take example of hydrogen gas reacting with iodine gas, giving you twice of Hi, which is also is a gas, hydrogen iodide. Now if the number of moles of these reactants are given and the vessel is having volume V in which these are taken, then definitely we will use the expression in terms of the concentration and we will call it Kc. It will be Hi, concentration of Hi to the square, concentration of hydrogen and concentration of iodine. And definitely what we'll be doing in this is, in this, number of moles of Hi upon V to the square, number of moles of hydrogen upon V and number of moles of iodine upon V. This is how it can be calculated. Suppose we are not given the number of moles of these reactants or the products, but instead we are given their partial pressures, then the expression will be expressed in terms of their partial pressure. Constant will be called Kp. It will be partial pressure of Hi, simple bracket, square, it will not be a square bracket, partial pressure of hydrogen and partial pressure of iodine. So this is its expression in terms of partial pressures. This is its expression in terms of concentration. And it all depends in the numerical that in what way the values are given and what exactly the numerical is asking. We can take one more example to make this point very clear. The example is the reaction of an ester with water in presence of catalyst sulfuric acid giving you acid liquid plus alcohol liquid. See, then this all the reactions and the products are liquids. It's a kind of homogeneous equilibrium. The equilibrium involved is called homogeneous because all these substances are in the same state. Now, since all these are liquids, all these will be having certain concentrations. They are not gaseous in nature. Their Kp cannot be expressed. We can only have Kc expression for such reactions. And it will be the concentration of the acetic acid formed into concentration of methanol formed upon concentration of the methyl ethanoate, the ester, into the concentration of water involved. This is what is the Kc expression is. So now I hope you must be clear about that for what reactions we can write the Kp and for what reactions we can write for the expression in terms of Kc. Another important thing, since whenever we are using the concentration in terms of whenever you are using the Kc, we must know that if we are having any solid or a pure liquid existing in the reaction, its concentration cannot be expressed because for expressing anything in terms of the concentration, we need to have a binary system, a two product system, and solids and liquids, pure liquids, cannot have a two binary system, two substance system. So their concentrations are taken as 1. Let me tell you one more example which will make this thing very clear to you. Like suppose calcium carbonate solid is decomposed and it gives calcium oxide solid and CO2 gas. If suppose somebody asks us that how can you write down its Kp, what is the expression of its Kp, we will write down only partial pressure of CO2, that's it. Because the concentration of the calcium oxide is a solid, calcium carbonate is a solid, they cannot have their partial pressures. Also, if somebody asks what will be its Kc, it will be only the concentration of CO2 because concentration of calcium oxide is taken as 1, concentration of CaCO3 is also taken as 1 because pure solids and pure liquids are given concentrations 1 because they cannot be expressed. The concentration need to have a binary system which these pure substances can't have. So they are always given the value 1. So this is the expression for the Kc in terms of Kc and this is the expression in terms of Kp.